8 co-authors asked for their own paper to be retracted. Not rival scientists, not regulators. The people who wrote the research looked at what was being published under their names and said, "This isn't right." That single fact tells you how much pressure has built up around one of the biggest unsolved problems in physics. In the next few minutes, you'll see what's actually at stake and why the real progress is quieter and stranger than anything that made headlines. The paper came from a physicist at the University of Rochester named Ranga Dias. It was published in Nature, one of the most prestigious scientific journals in the world, and it claimed a superconductor that operates at room temperature and near room pressure. The physics world stopped. If true, this was the breakthrough of the century, the kind of result that rewrites textbooks. Then, on November 7, 2023, Nature retracted it. 8 of the paper's 11 co-authors had formally requested the retraction, citing alleged data manipulation. The specific problem: the paper's plot of electrical resistivity did not match the description written in the paper itself. The numbers and the graph were telling different stories. You don't need an outside whistleblower when the research team itself fractures. To understand why careers are staked on this, why fraud risks emerge around it, why journals rush to publish it, you need to understand what superconductors actually do. A conventional conductor, like the copper wire in your walls, loses energy to resistance. Electrons bump into atoms, generate heat, bleed power. A superconductor has zero electrical resistance. Current flows without any loss whatsoever. One hallmark of this state is the Meissner effect. A superconducting material expels all magnetic fields from its interior. That's why a superconductor can levitate a magnet above it. Not a trick. A fundamental property of the material's quantum state. Today's superconductors already power MRI machines and quantum computers. But they only work at temperatures close to absolute zero, requiring liquid helium cooling systems that are expensive, energy intensive, and logistically complex. A superconductor that works at room temperature, without any of that cooling infrastructure, would be transformative across medicine, energy, and computing simultaneously. Lossless power grids, quantum computers that fit on a desk, MRI machines that cost a fraction of what they do today. That's the prize. That's why the pressure is this intense. While the Diaz controversy was still unfolding, a completely different claim arrived, not from a peer-reviewed journal, but from a preprint server. A group of South Korean researchers published papers describing a material called LK99, claiming it was a superconductor at well above room temperature and at ambient pressure. No exotic equipment, no crushing pressures. Videos of LK99 samples appearing to partially levitate spread across platforms within days. The term superconductor trended globally. Labs around the world dropped what they were doing to try to replicate the results. The levitation videos weren't fake, exactly, but they were misleading. The partial levitation turned out to be explainable by ferromagnetism, not superconductivity. Multiple independent labs failed to confirm the superconducting claims. LK99 wasn't the breakthrough, but it demonstrated something important. The hunger for this discovery is so intense that a preprint can trigger a global scientific sprint overnight. Away from the headlines, real progress is happening. Penn State scientists have developed a new method to predict which materials could exhibit superconductivity at higher temperatures, using computational tools to narrow the search space dramatically, rather than synthesizing thousands of compounds and testing each one. Meanwhile, MIT physicists have found compelling evidence of unconventional superconductivity in magic angle graphene, 2 layers of graphene twisted to a precise angle, a material that exhibits quantum behaviors that don't fit neatly into existing theoretical frameworks. Unconventional superconductivity is harder to explain. But historically, the materials that break existing models are often the ones that eventually yield the biggest breakthroughs. The Diaz retraction wasn't just a story about one bad actor. It was a stress test of how science handles extraordinary claims under extraordinary competitive pressure. Room temperature superconductivity is one of those rare goals where the potential reward in prestige, funding, and historical legacy is so enormous that it creates distortions. The incentive to be first can overwhelm the incentive to be right. The correction in the Diaz case came from inside the research team, not from the journal's editorial process catching the inconsistency. That raises real questions about whether top journals have the bandwidth to scrutinize data as carefully as the significance of the claims demands. Science is self-correcting. The retraction proves that. But the LK99 episode proves something else. In the age of preprints and social media, a claim can circle the globe before the correction has even been filed. The race for room temperature superconductivity is not a story of failure. It's a story of a field under so much pressure, scientific, financial, reputational, that it occasionally cracks. 8 of 11 co-authors looked at what was being published under their names and said, "This isn't right." That kind of internal collapse is rare. And it matters because it means the system, however imperfectly, still works. The breakthrough, when it comes, probably won't arrive with a viral levitation video. It will arrive quietly, survive replication, and then, only then, change everything. If you want more stories like this one, subscribe. The full article is on factstormhub.com.